Okay, so I guess we'll probably kick off. Just like to say thanks very much to the organizers of PyData for giving me the opportunity to speak today. I'm going to be speaking about recent attempts to marry Bayesian methods with deep learning. I'm going to be introducing a new probabilistic programming framework called Edward to do that, which was spun out of David Bly's lab at Columbia. I'm going to look at recent development which shows that dropout in neural networks, which I'll explain, is in fact a form of approximate inference. And then I'm going to actually compare experiments carried out using the black box variational inference in Edward with dropout. And I actually had no idea what the results would be when I submitted the proposal to this talk. So it's quite interesting for me too. I'm going to assume for the purposes of this talk that most people have some idea what a neural network is. So a neural network is a nonlinear function approximator. And we can think of a neural network as a parameterized function where the parameters are the weights and biases of the neural network. Typically, we will be passing our data through some kind of nonlinearity, like a sigmoid or a rectified linear unit. And often we can compose these nonlinear functions together, hence deep learning, deep neural networks with multiple layers of these function compositions. So I'm sure you don't need me to tell you that there's been lots of state-of-the-art developments for deep neural networks in all manner of data fields. Quite famously, we've also seen deep neural networks underpinning some work in deep Q-learning, which you saw to use to kind of play Atari 2600 or to play Go. Deep neural networks are difficult to train, but there has been lots of algorithmic innovations, things like stochastic optimization, things like dropout to regularize networks, which has made training on very, very large data sets possible. Of course, things like Python and TensorFlow as well, doing that sort of automatic differentiation. Okay, so what are the drawbacks of standard deep learning? And by standard here, I mean non-Bayesian. Well, in the first instance, neural networks compute point estimates of their weights, and therefore they make point predictions as well. They can therefore make very overly confident predictions about the particular class of an object, even if this is some sample that has been very far from the training data that they've already seen. So they can, very confidently predict in a very wrong kind of way. They have lots of parameters, so your kind of working industrial deep neural network can have millions of parameters, and this gives ample scope to overfit. So therefore, you tend to need very large data sets to try and offset this. They also have lots of parameters that need to be set, things like dropout probability, things like learning rate, et cetera. And all these things make life difficult. So the aim of probabilistic machine learning in general is to try and represent our uncertainty about predictions or about the models that we're using. So why would this be potentially significant? I mean, if you're trying to classify several million images, and your neural network misclassifies a few images of a cat as being a dog, it's probably not the end of the world. However, if you have an application where you have some important decision which needs to be made on the basis partially of a prediction of a neural network, you would like to know how uncertain your network is about its predictions. And you can think of obvious applications in things like a physician making a diagnosis in medicine, or potentially in finance, where you could have a trading model which is giving you a trading signal. Buy this asset. Okay, you'll say, well, how much capital shall I commit? How confident is this trading model in this buy signal? So you'd like to actually have some sort of uncertainty bounds, let's say, around your estimate. And this is really at the core of attempts to try to marry these Bayesian approaches with deep learning. So what is a Bayesian neural network? A Bayesian neural network is a neural network with prior distributions on the weights. So this accounts for uncertainty in the weights. You could think of your choice of prior as being like the range of the weights that you are willing to accept your network to have. Once you have this view of uncertainty about your weights, you can then propagate this into having a view on the uncertainty of your predictions. This also makes things very robust against overfitting, which is generally a kind of feature of Bayesian methods. In some instances, you can kind of infer hyperparameters by marginalizing them out. I'm not going to say too much about that. In the case of a Bayesian neural network, you have input data, X. You're trying to make some prediction on output data, Y. Your parameters are the network weights and biases. Now, typically, for Bayesian neural networks in practice, people tend to put normal distributions over the weights to reflect their uncertainty, essentially in the value of those weights. Okay, so trying to keep the equations to a relative minimum, but let's consider the general inference problem. You have some observed data. You have some latent variable whose value you are trying to infer. Now, in the case of a Bayesian neural network, your latent variable will be the weights of the network. And this is, of course, the famous Bayes rule at the top. I'm trying to update my prior belief about the weights in light of data that I've subsequently observed. So I'm interested in the posterior distribution of my weights given the data that I've observed. Now, the second equation here is really where the kind of magic happens as far as the Bayesian methods go. Let's say I show my trained network a new data point, X, and I want to make a prediction, Y star. What I'm essentially doing here is getting a distribution over my prediction. I'm sampling my posterior lots of times randomly. So if you think about what you're doing here, you're actually kind of summing over lots of neural networks with slightly different weights because you're sampling your weights from your posterior. So in that sense, you can kind of think of Bayesian prediction as being a form of ensembling over lots of models. This is an example taken from the simple Bayesian neural network example on the Edward website. So there's a simple cosine function here with a little bit of noise. You're trying to fit it with a Bayesian neural network. These are all neural network models with slightly different weights. And you can see you're kind of getting some measure of the kind of uncertainty in your model while trying to make this prediction. OK, but that's all well and good. But as we know, this kind of stuff is quite difficult. Exact inference is generally intractable. So you need to approximate this posterior. So this is always what we're trying to do in Bayesian inference. We want to approximate the posterior of the latent variable we're trying to infer. In this case, this will be the weights of a neural network. So in fact, this subject has a very, very long history. You can look back to the brilliant work of David Mackay in the early 90s. He published 4 papers on Bayesian neural networks, which made up his PhD thesis. The first attempt to do basically variational inference was by Hinton and Van Kamp in 1993. We've had groundbreaking work by Radford Neal and Hamiltonian Monte Carlo. And for people interested in this, there's actually a really great keynote address by Zubin Garamani at this year's NIPS conference, where he gives a very accessible account of the history of this subject. OK, so what happened here? Well, these methods were generally not scalable to massive data sets. And for actually a good decade and a half, the field went into some degree of dormancy until relatively recently. So for example, there's been a revival of Bayesian deep learning. This was the subject of one of the biggest workshops at NIPS in December in Barcelona. You can get some of the talks here. Some of it kicked off with this top paper by Alex Graves, where he came up with a practical Monte Carlo estimator for doing variational inference in neural networks. And again, there's a very good account given in Yaron Gal's PhD thesis, which was submitted towards the back end of last year, kind of traces the subject and discusses all these papers in more depth. OK, so moving on to probabilistic programming with Edward. So generally, probabilistic programming tries to represent probabilistic models, so probability distributions, as programs that generate samples. So in principle, any computer program with a random number generator can be a probabilistic program. The general idea is we're trying to infer some unobserved variables in the model conditioned on the program output. So you're running the program lots of times. You're getting slightly different random outputs. And you're looking at those outputs, and you're trying to infer some observed variable in the model. Let's say we've got lots of different probabilistic programming languages. The first 5 here, I think is probably fair to say, are more in the research language domain. Church and Venture, they're kind of probabilistic Lisps that came out of MIT. For the last 3, Stan, PyMC3, Edward, I think these are programs or probabilistic programming frameworks, which are probably more useful maybe to practitioners, to applied scientists, and data scientists. Now, one feature of a lot of these languages is they try to put the inference engine quite separately to the model. Now, the idea behind this is that a working programmer who's not necessarily an expert in Bayesian inference can just specify a model and then just pass the model into this inference black box that will just do the inference. The user doesn't have to be an expert. The user doesn't have to do a very model-specific type of inference. That's all well and good as a design principle, but in fact, for some recent developments in things like generative adversarial networks in deep learning, this actually creates a bit of a problem because the model's representation is actually reused in the inference process. So that could create a problem for maybe some of these languages like Church and Venture, but not so Edward. So generally, these languages will suffer from this kind of expressivity versus scalability trade-off. If you have something like Church, Venture, it's very, very expressive, but you're not going to be able to scale it up to very large data. And this is actually a quote which came up in my Twitter feed, which I quite liked, by Daniel Roy, who's one of the developers of Church. I think the context was a discussion about adding closures to Stan. He said all sufficiently complex PPLs eventually re-implement probabilistic Lisp. So on to Edward. Edward is a thin platform over TensorFlow. So Edward basically is TensorFlow, plus the addition of random variable classes, plus the addition of inference algorithms. So it looks and feels like TensorFlow as you're using it. So what is TensorFlow? We've already had a very good discussion of it, so I'm not going to spend too much time. TensorFlow is a computational graph framework. So if you think of something like NumPy, you might be doing a series of calculations. You're moving data to the C backend, and then you're pulling it back into Python, and then you're moving it back again. There's a communication overhead involved in all those transformations. In the case of TensorFlow, you just build this large graph of the computations you're going to do in advance, lazily, and only at the very end do you feed it with some data. TensorFlow is obviously quite geared towards the deep learning community. It's got a lot of functionality in that direction, but it does not by any means need to be used to do deep learning at all. You also have access to a lot of scalability, distribution. You have all these excellent stochastic optimizers, etc. So Edward basically adds these random variables as class objects. They have things like log probability, sampling, summary statistics. So how do you actually get a random variable into the TensorFlow framework? Well, if you consider a tensor in TensorFlow, you're just wrapping it with this kind of object. You're considering the TensorFlow tensor to be a sample from some random variable object. So it's a relatively simple idea, but it actually kind of gets the probabilistic programming aspect into TensorFlow quite well. And this is how you can define probabilistic models. So Edward has a lot of different inference algorithms, and under the hood, they can all leverage TensorFlow's excellent inbuilt optimizers, gradient descent mechanisms. So Edward, therefore, kind of allows this composition of models, which is a very common thing in probabilistic graphical models, for example. But you can also compile inference methods together, which makes it very, very flexible. So an example of why you would want to do this would maybe be something like expectation maximization algorithm, where you could have two different inference engines running simultaneously. Very importantly, of course, we allow data subsampling, so we can do mini batching, we can do stochastic optimization, and that allows you to scale this up to very big sizes in terms of data set. So Edward's general philosophy, this is where the name Edward actually comes from, the statistician George Edward Pelham Box. So the idea here is, you specify a model, then you do some inference on the model. But what if your model is misspecified? Well, you'd like to be able to go back and do some predictive checks after you've done your inference, whether you can reproduce features of the data. This is very integral to the general design framework of Edward. And it's described in these two papers here. Dustin Tran is the lead developer. He's a graduate student of David Bly's at Columbia. OK, so what does Edward actually look like? Well, this is a two-layer neural network in TensorFlow. I'm using Tanch activation functions here. Now, in the case of Edward, we're doing probabilistic programming. We'd like to have priors over our weights. And this is basically how you add them. So it's looking quite TensorFlow-like overall. OK, just very quickly, again, the general inference problem, you have some observed data. You have some latent variables that you're trying to infer. and then you have some posterior approximation to those variables. In Edward, you're just going to bind your weights to your posteriors, denoted by QW for the weight, QB for the bias. Similarly, for your data. And then this is the sort of very simple interface you will use to actually do the inference. You have your latent variables that you're trying to infer. You have your data. And then you select some inference algorithm, which is built into Edward. So they all inherit from this inference class. It can be variational inference, Monte Carlo. It's got a lot of things in there. This abstraction can represent a very broad class of models. So I think the sort of interface in Edward is quite terse, and it kind of works quite well in that respect. OK, so the thing I'll be looking at in particular will be variational inference. Again, if you think of variational inference, you're trying to approximate the weight posterior. Variational inference works by positing some approximate posterior, parameterized by some parameters theta. You're trying to make this approximate posterior as close to the actual posterior as possible. You're trying to minimize the divergence between the two by sort of turning the little dial of your parameters until you pull the approximate posterior as close to your posterior as possible. Typically, for reasons of computational tractability, a mean field approximation is often used. What that means essentially is each of your weight layers are considered to be independent of each other, and that they don't interact. I think that this might actually cause problems later on down the line with some of the very high-dimensional neural networks, but I'll show you those examples later. Unfortunately, minimizing this divergence between your approximate posterior and the actual posterior is hard because you have this evidence term, which is one of the reasons you're doing approximate Bayesian inference in the first place. Fortunately, with a very minor bit of equation shuffling, you can come up with this other quantity, the evidence lower bound. Minimizing the divergence between your approximate posterior and the actual posterior is the same as maximizing this other quantity called the evidence lower bound. The evidence lower bound consists of these two terms. The first one tries to make sure that your approximate weight posterior is giving you good samples that look like they explain the data quite well. And the second term is ensuring that your approximate posterior is not going off doing its own thing too much, that it's close enough to your priors. So this is like a term that penalizes excessive complexity. It's like an Occam's razor term, you could call it. OK, to optimize the elbow, we want to maximize it, so we need its gradient. One of the innovations of the so-called black box variational inference is that you can estimate this gradient using Monte Carlo sampling. So you don't need to actually have any real knowledge of the model that you're using. This is a very generic type of approach that will work for the elbows of any model, pretty much. It's a black box approach. It makes it very, very scalable. One of the problems, of course, with any Monte Carlo estimation is that the gradient estimation can be quite noisy. So what Edward does is you showed a model. It automatically selects from a lot of black box inference techniques. So you just decide, I want to do KLQP is the name of the class. And then you don't really need to worry about it because Edward will try to optimize this as best it can using these black box variational inference techniques. OK, so changing tack a little bit, we go back to the idea of deep neural networks in particular. Now, one of the big developments in neural networks was in 2014. This paper is Srivastava, Hinton et al., where they find a way of regularizing neural networks using Dropout. So literally what they're doing is they're taking the weight matrix of a neural network, they're multiplying it by some binary vector of ones and zeros, where the probability that an entry is 1 is given by a Bernoulli distribution parameter p. And where the binary vector value is 0, you're basically just switching off or dropping out the hidden unit in that particular layer. So during the training, you're doing this lots of times. So what you're doing is you're showing you're passing the data through a slightly different network every time. And this prevents the network from co-adapting too much to your particular data set. So it greatly improves out-of-sample performance. And it's generally been a very, very, very big development that's allowed training in much larger neural networks and data sets. OK, so, well, how's that related to variational inference? Well, I mean, if you think back to my earlier point about the predictive distribution, you're kind of randomly sampling from a posterior over weights. So you're kind of averaging over slightly different neural network models with slightly different weights. That sounds a little bit like what you're doing with Dropout. Let's say you have a loss function. This is for a neural network. Your loss function could be mean squared error in the case of a regression problem. You have some regularization, and you're assuming that your network has been trained with this dropout capability. What Yaron Gal, who was at the time a graduate student of Zubin Garamani at Cambridge, showed in 2015 was that you could reparameterize this variational distribution, this elbow thing, and that you could actually make it look a lot more like a dropout objective. I mean, essentially, to not go into the detail of it, they show that your variational inference objective and a dropout neural network objective are in fact the same formally. Now, the proof of this somewhat involved, and it calls upon the theory of Gaussian processes. So I'll just say this about it. A Gaussian process, as shown by a result of Radford-Neal in the early 90s, essentially a neural network with a single layer that's infinitely wide with Gaussian priors and all the weights is a Gaussian process. And that was basically the sort of the undertone to this kind of work. So we don't need to talk too much about that because I want to get on and show the results. But essentially, optimizing any neural network with dropout is equivalent to a form of approximate Bayesian inference by this reparameterization of Gal and Garamani. A network trained with dropout, just a standard network that maybe some of you have used already, is a Bayesian network. OK, so that's all been a lot of theory. But how do you actually implement this dropout as Bayesian approximation in practice? Well, essentially, what you do is you're applying the dropout layer at test time. So you're taking your test data, you're running it through your trained neural network, you're applying these dropout filters at test time. Now, that's not typically how dropout has been applied in the past. Generally, dropout was quite an ad hoc empirical technique, and practitioners tended to apply it at training time, and at test time, they would just use a sort of weight averaging. So here again is our old friend, the predictive distribution again. We are taking our test set X, we're firing it through the neural network to get an output Y, and we're getting a different Y every time because we're applying a different dropout filter. So actually, if you keep doing this lots of times, you do T stochastic forward passes through the network, and you start to actually get this distribution of predictions Y. Now, that distribution effectively is the Bayesian predictive distribution that we saw at the start of the talk. So if you want to estimate, rather than get a point estimate from your neural network, you can now get a predictive mean and a variance around that by simply collecting the results of these stochastic forward passes through an existing neural network trained with dropout. So clearly, if your model is more uncertain or you have a lot of predictive uncertainty, your neural network predictive distribution will be wider. OK, so I'd just like to say that this has also been very successfully employed in a range of different architectures to get state-of-the-art results, for example, on CFAR10 and convolutional neural networks. Similarly, getting very impressive results for recurrent neural networks on the Penn tree bank data set and also in reinforcement learning. OK, so what I wanted to do was compare essentially the same Bayesian neural network trained using black box variational inference in Edward with one trained using this MC dropout, which is the generic term that they use. I looked at a feed-forward neural network with 2 hidden layers and 50 units per layer. Now, the reason I did this was because this is what was used in these 2 publications. The first one was by Hernandez Lobato and Ryan Adams. They used an inference method called expectation propagation. And the second is the original MC dropout paper by Gal and Garamani. So they used about 10 publicly available benchmark data sets. You can use the code. This is what I used to use MC dropout. After a pull request, it's actually possible to do this in Keras. So you can actually run MC dropout straight away in Keras. And this code was based on an earlier code by Hernandez, Lobato, and Adams. OK, so here are my results. So again, I had no idea what would really come out of this when I submitted the proposal to PyData, but we have a series of data sets on the side. For example, Boston Housing tries to explain the price of Boston Housing against 12 other explanatory variables. Some of them are categorical, some of them are continuous. So what we have here is the root mean squared error. So we want this obviously to be low. Low is good. For standard dropout, which is how practitioners had applied dropout before, you train your network with dropout, and then at test time you do a single pass through with all the weights averaged. You see some of these results. MC dropout, which is where you, at test time, multiply run your test set through the network many times with dropout switched on, does better in every single case, sometimes substantially better. Now, BBVI is what I call black box variational inference, which is what's currently implemented in Edward. For a unit 50, for a network 50 units wide, it's actually not terribly good. What I did find that was interesting was when I dropped the width of the network from 50 to 10, therefore making it a lower dimensional problem, I got some improvement. And at least in the case of the yacht hydrodynamics data set, you're seeing improvements or you're seeing results which seem to improve over standard dropout, at least. I should add that these are very small data sets. Ideally, you should be probably shuffling, making lots and lots of splits, and running this several times and averaging over the results. So these estimates are going to be very noisy. I would take this to be a very much ballpark kind of comparative indicator. So there could be if you ran this again, I'm saying you could get these numbers jumping around quite a bit. So that's probably good practice to do this. At the bottom, the test log likelihood is just a measure of how well our model fits the data. So you want these numbers to be less negative. Less negative is good. And again, you see the results here. MC dropout is generally looking pretty good. Black box variational inference with 10 units doesn't look too bad either. Yeah, so what's going on here? In the first instance, we should admit the primary possibility that I've done something wrong in the modeling. If that's not the case, then we should think about the kind of approximation that black box variational inference is using. If anybody was at Padre Coyle's talk yesterday, they'll see I've shamelessly plagiarized this chart from his excellent repo on Advanced PyMC3, so I think you should definitely check that out. But yeah, Edward is using mean field variational inference. So the assumption is actually that all the weight layers are completely separate. They're not correlated. There's no interaction between them. I've seen a good description in a paper by Luizos and Welling where they say if you're doing mean field approximation, you have a unimodal bump in the very high dimensional parameter space of the neural network. But maybe the real posterior is quite multimodal. It might have lots of peaks. And maybe the mean field distribution, particularly at high dimensions, is just simply not flexible enough to capture the real posterior. This is my own summation. On the other hand, MC dropout, though this is very far from obvious, gives you a posterior which is multimodal. So it may be that MC dropout is just managing to capture the real approximate posterior, a little bit better. Since submitting this, I also came across a paper by Luizos and Welling where they actually run another form of Bayesian neural networks on the same data sets that I just have there, where they try to include some sort of correlation between the weight layers. And their results, most of the time, are actually better even than MC dropout. So it again lends credence perhaps to the idea that you need to include some correlations, and they become increasingly important as you increase the dimensionality of your deep neural network. So I use 2 hidden layers. That's probably the minimum that you could possibly call deep neural network. But again, my motivation was in following the papers that I quoted. So this could be the next research direction really for variational inference. There's a lot of work going on in making better and more flexible posterior approximations that go beyond the mean field approximation. Normalizing flows, if you heard Padre Coyle yesterday, that's currently being worked on to go into PyMC3. And another very active area of research is in making these Monte Carlo estimators of the elbow less noisy. And I'd just like to say this work was done by me as a fun project in a personal capacity. But I work at a brokerage called Prism FP. We have offices in London and New York. we are in the process of spinning out a new fintech company, Prism FP Analytics, which is going to be doing sort of next generation analytics for the asset management industry. And I'm looking at some interesting research there, including some Bayesian models. It's so stealth mode that we don't have a website just yet, but by all means, if you're interested, please grab me at any point today to discuss further. Thank you very much.
10 minutes for Q&A.
Perfect timing. Yep.
Hi, thank you. Really excellent talk, which I thought I understood all of until you got to the results.
Yeah.
I thought that your goal with this was to get probability estimates, confidence intervals or similar around the predictions.
Yes.
But what you seemed to do when you compared the different techniques was just to compare RMSE.
Yes.
So I was expecting you to say, maybe the overall performance is similar, but in the areas where it had strong confidence, the results were really good. But in the areas where it had low confidence, maybe they weren't as good. Did I misunderstand? Or?
No, I think probably it's definitely a presentational issue on my part. I should have included an example, perhaps, that has a lower dimension that can be plotted quite easily. I could look at a one-dimensional function and plot the uncertainty bands around it. These problems were all quite high-dimensional, so it's quite difficult to represent the uncertainty estimate quite clearly. If you look at the original paper by Gal and Garamani, it gives you a good kind of idea in the context of, say, the MNIST data set. They take the digit 1. It's classified with a very high degree of confidence. They then start to spin the 1 around, and you can see the model uncertainty estimates expanding as it moves towards a digit which the model hasn't seen before. And it starts to misclassify it as a 3, but the confidence intervals are very wide. So if I had a bit more time, I would definitely like to have included something along those lines in the talk.
Your first example was the Boston housing data, right? Aren't you predicting a single price for each input there? So
you are. I mean, there are. You can get confidence bounds around those as well. I just didn't include them essentially, and they're partially because they're not included in the original data set. It was just trying to show, I think, that I guess the anti-overfitting capability of the Bayesian neural network is very useful. So I have kind of tracked that paper as closely as possible, but it's definitely something I would like to look at more. I should also say again, I would emphasize that they ran this 20 times and got a big standard error over that, which I didn't include.
Quick question over here. Hi. Thank you so much, again, for a very interesting talk. I really like the idea of the MC dropout. Would you mind explaining how the parameters of the Bernoulli distribution were estimated and how robust your inferences to...
Yeah, I mean, they didn't try to do any fancy estimation of the P, the estimation of a unit being dropped out. They used P of about 5%. Now, there is another paper by Kingma and Welling where they try to actually do a sort of Bayesian marginalization of that P probability called variational dropout, where they try to estimate that using a Bayesian inference as well. But as far as I know, this paper, they did actually find also that the results were quite sensitive to your choice of P. So for some cases, moving from a P of 1% to 5% did actually have quite big impacts on the accuracy of the RMSE afterwards. No, I took the values straight out of these papers, and these papers didn't specify exactly how they came across the P. There is another parameter they used, the tau, which is the model precision, and they actually estimated that using Bayesian optimization. But I just assumed that was a fixed parameter from their paper.
Yeah, a really interesting result. I was just wondering, maybe related to the last question, when you do this sort of MC dropout, can you give some guidance on the number of samples you need to get some robust statistics? Or does that vary quite a lot?
The examples they gave about 10,000 forward passes through the network. So that obviously slows things down.
Yeah, so that was the
training stage is exactly the same. You have a trained network, that takes the same, but the test time is scaled up by order T, the amount of stochastic forward passes you need to do. So they did 10,000 for these data sets, and I just basically ran Yaron's code.
Great talk, cool. Just out of sheer pragmatic reasoning, sometimes you could still use PyMC3, sometimes you might want to consider Edward. Is there any advice on when you would use either package? Because they seem to be doing similar things at some point.
Yes, I do. I mean, Edward has this ADVI, which is probably like, next generation black box variational inference. That is currently going into Edward at the moment. PyMC3 is also trying to put in this normalizing flows after the work of Rajenda and Shakir Mohammed. So that should also, make better variational approximations. I haven't actually benchmarked them, and that's actually the next thing I want to do. I want to actually run a load of benchmarks for some of these other systems, ADVI, et cetera, and make them public. Maybe it would be useful for that reason.
Hey, over here.
Oh, hello.
Thanks for the great talk. I was wondering, so if you compare this method to, so when we build an ensemble models of multiple train neural networks, it's kind of the same, right? Although they're all like maximum likelihood points. But we could have trained an ensemble and then run, say, a couple steps of HMC on each of them. And hopefully all of them are like Bayesian posterior samples, all from like they're not going to be suffering from like being in the same mode as if I were running just one chain of HMC.
Yeah.
Would that work better? Like, do you expect that would like compare? Like, so both like without HMC at the end and with HMC at the end, how would that go?
Yeah, I mean, I think there was a paper I referenced in 1998, Barber and Bishop, where they used a sort of ensembling approach. It's difficult to tell, really. I don't know what the accuracy versus the speed up trade-off would be of using variational inference. The honest answer is something I'd like to try, but I don't know yet. I mean, generally the idea would be variational inference will be a little bit quicker than some of these approaches, but I don't know what the accuracy trade-off is.
One last question.
Yeah.
Hey, quick question. So, if you train a neural net, let's say, to diagnose whether someone has cancer from CAT scans, and you get, let's say, 95% classifier accuracy, what's preventing us from using that as the confidence interval, as a fixed confidence, and say, like, when I'm making a prediction, it's 95% accurate instead of doing the Bayesian approach?
Yeah, you can. I mean, this is kind of like the idea behind the Bayesian credible interval. A confidence interval is like a sort of frequentist analog of credible interval. So, yeah, I think it's reasonable to use it in that kind of way. I think the credible intervals in Bayesian methods correspond quite well to our intuition about, well, I'm uncertain of how accurate my measurement is, so this thing gives me bounds around it. Yeah, I think you could definitely use that in a principled way.
We have time for another question.
Is that somebody in the corner?
How do you calculate the confidence bound when you stack layers of networks, or how do you, when you use ensemble models? Was that heard from there?
When you stack things together, well, I mean, ultimately you're looking at, I mean, the amount of layers doesn't necessarily matter. You're putting your test set through the network, and you're getting out a single prediction at the end with dropout turned on. You're doing this lots and lots of times, and then you're beginning to get lots of Ys. You can take the mean of those. That will be the mean of your predictive distribution, and you look at the standard deviation to see how uncertain you are.
But without this technique that you mentioned that you turn on, this initial way of doing it?
Which was that, sorry?
Without the multiple passes?
Oh, yeah. So if you do it without multiple passes, you can't really get the uncertainty estimate. So that's the way that standard dropout is actually used. It was described in the Srivastava and Hinton paper as weight averaging. So they train the network, but when you do a single pass through the network, you kind of basically assume the weights have been averaged somehow. So you can't get an uncertainty interval because you're only getting one prediction.
Okay, thank you, everyone.